Thank you. Hello, everybody. To the webinar for Principles of Electroacoustic Sound and Loudspeakers, as Nelson said. So the topics we're covering today are what is electroacoustics, how it works, loudspeaker basics, how room acoustics affect sound and intelligibility, key characteristics of electroacoustics, and planning for the Electroacoustics PA system. So what we're going to talk about is what electroacoustics are, first of all, which is a science that deals with the transformation of acoustic energy into electrical energy or voltage and vice versa. And it's also the recording, transmission, and reinforcement of sound. So basically, the principles of electroacoustics can be seen with any device in which you can play recorded sound through a loudspeaker, and such as mobile phones, audio systems, or Bluetooth headphones. It's the equipment that allows for the transformation of acoustic energy into electrical energy. That's called a transducer. What transducers do is translate between acoustic domain to electrical domain and back. There are two main types of transducers. Although the transducer itself can be built differently, the concept and process is the same. So in electromagnetic, there's a transducer for non-acoustic wave generation and reception and conducting materials. It uses the interaction of a current, so basically a copper wire that's wound around the voice coil that moves in a magnetic field that it's creating. Most loudspeakers are of the electromagnetic or a dynamic variety, in which a voice coil moves in the gap of a permanent magnet, which when a time-varying current flows through the coil. So just basically when you add electricity to it. So there's electrostatic. It's the types of transducers. It's a transducer with a charge capacitor allowing one of the capacitor plates to vibrate. The sheets create sound in loudspeakers and microphones. And electrostatic loudspeakers make use of a large thin metal plate between two parallel screens, and amplified audio signal is then impressed onto the screens, polarizing the metal sheet, and the resulting electrostatic force creates a motion of the plate, producing a sound wave or audio. So if you know your basics, when the sound pushes out, that's your higher frequencies, and when it pulls back, that's your lower frequencies. So if you look at this graph on the bottom, the air molecules, as represented in the slides, represent truer. It's a truer depiction of what the air molecules are actually doing, as opposed to the sine wave at the bottom. The sine wave is good for drawing and mathematical equations, but the air molecules at the top in this particular drawing just reflect more reality. If you can see air molecules, that's what they're doing when on the way to your ear, when the sound pressure gets to pushing the air. So basically how sound is captured is air molecules vibrating between high and low pressure are captured by the microphones. Microphones take those high and low pressure fluctuations and convert them into analogous fluctuations in voltage or an analog signal. When the pressure gets high, the voltage gets high, and the pressure is low, the voltage is low. These analog signals can pass through wires that conduct electricity, and then a loudspeaker on the other end can convert these changes in voltage back into acoustic energy and vibrations in the environment. You can also take those changes in voltage and record them onto analog medias, like a magnetic tape, for example, and play back later. The third option is to take those changes in voltage and change them into digital information, but that requires another step. So an analog to digital converter is a system or device that converts analog into digital samples. The process involves the conversion of analog into a series of ones and zeros, so bits and bytes. The last step is a conversion back using a digital to analog converter, which to play on the loudspeaker, which you can see in the process in the drawing at the bottom. Okay, so we'll go to the next slide. So another one is the Bluetooth. So analog sound traveling wirelessly to the Bluetooth headphones is converted to digital, transmitted to the headphone, where it's converted back to analog to be played by the loudspeaker in the headphones. So this is just the basic makeup of a loudspeaker, and a current is sent through the voice coil, which produces an electric field that interacts with the magnetic field of the permanent magnet attached to the speaker. Like charges repel each other, and different charges attract. As an audio signal is sent through the voice coil, the musical waveform moves up and down. And the voice coil is attracted and repelled by the permanent magnet. This makes the cone that the voice coil is attached to move back and forth to create the pressure waves that we perceive as sound. And then you can see the drawing at the bottom, basically how it works. There's also I found a good video, if you all want to look it up later, by a guy named Jake O'Neill from Animagraphs, that says how speakers make sound. It's a really good overview of what the speaker is doing exactly, if you want to look that up later. So loudspeakers come in different shapes and sizes, perform different functions when creating sound. It's challenging to make a single speaker to cover the full frequency range that humans can hear, which can go as low as 20 hertz to 20 kilohertz. Obviously, well, it might not be obvious, but as you age, the frequencies you can hear get smaller, so that gap gets smaller and smaller, which is why intelligibility and mass notifications systems is important. For that reason, to deliver the best sound, a variety of speakers are used to cover the entire frequency range, or as close to it as possible. Example of two loudspeakers together that cover the most frequency range. It just shows you on that graph there on the bottom. So just the mixture will cover that gap in the middle between the red and the blue line. So this is just how sound works in rooms. So if you can imagine, most standard meeting rooms are cubes. So when sound is released in a room, either through a speaker or voice speaking, the intelligibility is affected by the directivity. Direct sound versus reflective sound, which is reverberation. Sound does reflect off the wall and ceiling, causing sound to reach the ear after the direct sound. And reflective sound is bad because reflective waves create destructive interference patterns that change in the original sound wave. The original sound waves are distorted by later arriving reflections. One sound traveling really fast, causing up to 60 reflective bounces off the wall in 1 second. So now imagine if thousands of reflective bounces interfering with the direct sound, the distortion would be tangible. For example, in our showroom, or the boardroom where I'm speaking to you from, we just put acoustical treatment in here, so we don't hear any of those reflections anymore. So we've got our ceiling tiles and our walls covered in acoustic treatment, and sound can't be heard outside of this room anymore, and you can't hear a reflection from a clap like that, which is cool. So one thing that we do that's part of my job as part of TOA's design team is we overcome the issues of intelligibility by creating audio layouts with modeling software, such as you see Ease Focus on the bottom right. It's a complimentary service that we provide upon request. We also use our speakers, these line arrays, as you can see. We can direct them to project the sound where we want to go. These are like our HX5 line arrays, or HX7, and the SRT5 is pictured on the top right. And they're all really good pro level speakers. So sound characteristics, whether it's a shopping center, sports stadium, or retail space, the acoustics of a space determine how the visitor perceives that space. A room's practical usability is also determined by its acoustic parameters. At TOA, we have made it our mission not only to provide you with high quality equipment, but above all to deliver superior sound. So the next pages have details that are some of the key aspects of sound and equipment to consider when planning and installing a PA system. So I mentioned this a couple of times. The magnitude of the pressure variations is referred to as sound pressure. So the unit of pressure used to measure the magnitude is normally in decibels. In practice, it is more advantageous to deal with sound levels using decibels. As a result, decibel levels as sound pressure levels are unambiguous and can be compared to each other. So this is frequency response. The frequency response is a number of oscillations per second, which determines the pitch, and it's measured in hertz. So 1,000 hertz is also referred to as 1 kilohertz. That's the sound from back in the day that people in broadcast television call test tone. So if you know what that sounds like, it used to come when TVs used to turn off at night. That would be the tone that you heard. Electroacoustics deals with the audible frequency range from, as I mentioned before, 20 hertz to 20 kilohertz. So room acoustics relate to the effects of a room's structural conditions on the acoustics. Room acoustics have a major impact on how the visitor perceives a room. Therefore, it also plays an essential role in electroacoustic systems. So there's the consideration of the direct and indirect sound or ambient noise. So sound spreads out radially from a source. So some of the sound waves reach the listener directly, while some are reflected by the walls, ceiling, and floor, and still others are absorbed, depending on how the room's configured. So if you're talking about reverberation time in a very reverberant room, you need to consider that, because a very reverberant room can diminish your intelligibility and your ability to understand the sound or what's being said. So when sound stops, indirect sound remains in the room for a short time as reverberation. The reverberation is defined as the time that elapses until the sound pressure level has dropped by 60 dB. Reverberation time is closely linked to a drop in speech intelligibility. So the basic rule is that speech intelligibility deteriorates as the reverberation time increases. So if you think of like a hockey arena or something like that, where people practice playing hockey, that's inside that, and the sound's really bad in there, whether there's like when you're just speaking, you can hear reflection of your voice, like a bad echo. That's from a very reverberant room. So it is critical to convey as much direct sound from the loudspeakers to the listeners to minimize reverberation. And on our configuration software or modeling software, which is EZ back in Ease Focus, they're called RT60 times, and they're considered in something like a hockey arena. So how TOA products can help, as I just mentioned, our technical team prepares a design with the proper placement of speakers and other equipment using what's called the Ease EVAC system or Ease Focus. We use Ease Focus for line array speakers of various shapes that can be installed and adjusted to ensure the sound is direct to the audience. Employing one of our reliable mixers with the ARC function, which enhances sound clarity when reducing reverberation. ARC stands for Automated Resonance Control, and it's really helpful. Adding other TOA equipment such as DSP, a digital signal processor, will help complement the system and just make it sound better. So this is just a list of loudspeakers and their specs. Loudspeaker types are designed for both general and specific applications and therefore have different executions. We have broadband loudspeakers, which is one that can reproduce at least the main portion of the audible range of hearing. Multi-way loudspeakers, 2 or more loudspeakers are combined. Each individual loudspeaker is designed for a specific frequency range, so everything gets hit. Like if we put HX5s with a subwoofer FB120, the result is that a larger frequency range is covered. Horn loudspeakers, they're focused on amplifying the sound waves, and horn loudspeakers are highly efficient and can achieve high characteristic sound pressure levels. Then the line arrays, which I mentioned previously, generally have a wide horizontal coverage angle and a narrow vertical coverage angle, and so that's why they're piled on top of each other, basically. When oriented properly with respect to the audience, only a small portion of the sound will strike reflecting walls and ceilings, generating little reverberation. So a little more on loudspeakers and their specifications. So the rated power, which is measured in watts, indicates that the electrical power that the loudspeaker is able to draw in continuous operation. The rating is referring to how much power the speaker is designed to safely receive from an amplifier before it will start to distort. And then power or tapping for our high impedance loudspeakers, the 70-volt loudspeakers typically often allow for the power to be adjusted to values lower than the rated power. So it is frequently possible to tap the power down to 1/2, 1/4, or 1/8 of the power. And that makes it possible to adapt the volume of the speakers to their surroundings. So then impedance refers to the AC resistance of the loudspeaker. There are two types, low impedance and high impedance. So low impedance are 8 ohm, 16 ohm, 4 ohm. They're all referred to as 8 ohm typically. And high impedance can vary, but typically are 25 volt, 70 volt, and 100 volt. In Canada, we tend to use 70 volt. In the EU, we tend to use 100 volt. If we're using 25 volt at a high impedance, that's usually because we're doing half duplex communication in a school or something like that. So the speaker can be utilized as a microphone to talk back to a master station. And then sensitivity is the measurement at 1 watt of supplied power at a distance of 1 meter. That's called sensitivity. There's no uniform notation that's been defined, but the general convention is something like, for example, 96 dB measured at 1 watt at 1 meter. That's pretty standard across speakers with ourselves and our competitors. Frequency response is the range that the loudspeaker can produce, e.g. 50 hertz to 20 kilohertz, or in the form of graphical representation, which is what's the little graph on the right-hand side that you can see. So calculations with loudspeakers. So when you're designing an audio system, there are calculations and tables that are used to assist with loudspeaker selection and placement. The sound pressure level at a defined power, you can see in the graph there. Loudspeaker datasheet provides the information for sound pressure levels that I mentioned before. 1 watt at 1 meter. This one's 95 dB, so it's 1 dB different. It means that 1 watt of power, the loudspeaker generates a sound pressure level of 95 dB at a distance of 1 meter. And then the following table indicates how many decibels the sound pressure level of the loudspeakers is increased at a given power. So like if you want to go up one step, if you go to 2 watts from 1 watt, you have 3 dB increase, and then at 5 watts it's a 4 dB increase, and so on. You can see the graph, and it's just math and physics, but each doubling of power gives us an additional 3 dB of SPL. There's a mathematical formula at the bottom that will calculate that yields the same result. So P1 equals Pn divided by 10 times the log times the power. And then a little more calculations with loudspeakers. Sound pressure level at a defined power. If you would like to calculate the sound pressure level produced by the loudspeaker, not at a distance of 1 meter, but at 6 meters, there is a table and a formula for that as well. And then this one's a little different. So with distance, with each doubling the distance, the sound pressure level drops by 6 dB SPL, and conversely the other way. And then there's another mathematical equation at the bottom to show you the same result. P equals P1 minus 20 times log times D. And then more calculations. So this is the graph for intelligibility. So P for a public address system with ceiling loudspeakers. So the distance and minimum sound pressure level between TOA standard loudspeakers at loudspeakers public address. It's worded a little weird, but that's okay. With ceiling different degrees of speech intelligibility over 6 watts of power. So basically that's showing your ceiling height and the distance between loudspeakers and the minimum sound pressure levels in that graph there. You can like read it and refer to it. It just, it sort of tells you that the top 2 lines are for best intelligibility. Then if you want good intelligibility, it's the second set of lines, and then just for background music, which is a little more forgiving, that's the bottom 2 lines. So planning for electroacoustic systems, you can see on the bottom chart there is a example for the MA 725 head-end system with that's connected to a Wi-Fi router and some controls, a EM380 music source like a CD player, and then you can see all the speakers in the center there, which are mostly pendants, a few ceilings, and two wall-mounted speakers, and that's divided into 4 zones. So basically, the public address systems are usually set to mono. They typically distribute 1 or more audio signals into different areas that we call zones. The type of audio signal can either be background music, manual or automatic announcements, or signal tones, which can come from modules or the EV20R or EV700, which are digital message announcers. The audio signals are normally not mixed. An audio signal is transmitted into 1 or more defined zones. Priorities are assigned to avoid the inadvertent merging of different audio signals. For example, if multiple announcements are to be broadcast in the same zone at the same time. So most PA systems, when we design them outside of the pro level line arrays, are high impedance loudspeakers, but we do have matching transformers, so you can actually run our pro speakers at 70 volt. So types of PA systems. There are central PA systems. For a central PA system, speakers are all installed in the same location, i.e. in the middle of a hall ceiling. Frontal PA system, if the sound is accompanying an optical event, the sound should also be originating from the direction of that event. So that would take place in the front of the room normally, like with a stage, for example. The loudspeakers are usually positioned to the left and right, and in certain rooms it could be necessary to install loudspeakers along the wall, like as delays or fill, or even the ceiling. The large event rooms need sound to be adjusted to take into consideration the sound delay to reach the back of the room. That's what I mean by a delay speaker. They're usually offset by a fraction of a second, so the sound reaches everybody at the same time. And then when we're talking about a decentralized PA system, that's a system in which the loudspeakers are installed where they are needed. The ceiling loudspeakers should be distributed evenly over the PA system's effective area, generally in the same spaces between all the loudspeakers. The higher it is possible to mount the loudspeakers, the greater the effective range of the loudspeakers, and therefore also the acoustic range at ear height. For good intelligibility, the frequency response of this system should be able to reproduce signals of up to 6 Hertz at every point in the audience area. So on planning for electroacoustic systems, choosing the correct speakers for a project is usually based on the size of the area to cover. With a small space, utilizing low Z speakers, so 8 ohm speakers when working with larger areas, high speakers are preferred to minimize the loss. So low impedance systems, it is important to remember that the total impedance connected to the loudspeakers may not be less than the minimum terminating impedance of the amplifier. Systems can be connected to speakers in parallel formation. Serial formation is not normally recommended, and you can see an example of 2 8 ohms connected in series, which would be okay for a 4 ohm amplifier, although it says it's not recommended above it. And then there's the chart on the bottom right there. 8 ohms or low impedance in a range of approximately 2 ohms to 16 ohms. It's ideal for high power speakers, high performance, short cable runs used in systems like a nightclub, house of worship, restaurant, bar, patio, home stereo, and in my experience, live events. So this is planning for high impedance technologies in a PA system designed for large areas, like a MES, like a distributed PA, like in an office building or multi-zone, like 1-floor building that's very large. You'd want to use a high impedance system to minimize signal loss over distance. So in a PA system designed for large areas, high impedance technology is preferable in order to minimize line loss. Different areas can have differing sound pressure levels achieved using a single amplifier. For example, with these parallel connections, that example, you can have all those speakers tapped at different wattages, as long as you're not exceeding the total wattage of your amplifier. By you usually want to have 20% headroom, so total wattage times 1.2 to add 20%, and as long as you're below that, you'll be fine. So 70 volt high impedance is referred to, as I mentioned earlier, 25, 70 volt, 100 volt, ideal for lower power speakers, many speakers per line speakers that have adjustable power taps, high impedance output, and there's less amps required. Used in applications including public address, corporate, commercial, industrial, and education. So if you have any questions, you can ask in the chat or unmute, and we will. I can do my best to answer them.
Hey, sorry, just a quick question about sublocation. So we in our gym areas, we've been putting in the SRT5s, and some of them, some of the schools have been asking for more oomph, and we've been adding in the subs. We've seen subs where we put them right beside the speakers, directed to the audience, or we've seen it right where beside the right in the corner of the walls, so they reverberate off of two more walls. I've tried to get a straight answer from some of the guys, but I haven't really had anything. But do you have any thoughts on that?
So you said you have SRT5s. So where are they located on the walls? Are they on the long wall or the short wall?
It depends on the gym, but for example, this is say on the long wall.
Okay. Sometimes what we do is we just put them right on the floor underneath where the SRT5 is, in order to just so it feels like it's coming from the same place as the SRT5s.
Okay, yeah, no, sorry, we try to avoid it just because the kids and stuff would obviously create
Yeah,
tripping
I
hazard
get
and
you.
all that stuff. Yeah.
I don't. I can. I can write your question down and ask my supervisor what he thinks about that. But that is normally what we do. The SRT5 is a little different because you don't have the rigging frame.
Yeah.
So
No,
that could be an option too, is to get a rigging frame and fly it near the SRT5. But you might need a cage for that too, to protect it from ball strikes.
no, for sure. No, we have a welding shop, so we create a little bracket. Like I said, so we have the SRT5, and then we have we create a little frame for the bass bin, and we usually put it right beside it. But again, I've seen it kind of right beside the speakers pointing towards the audience, or I think I just want to see what would be the optimal placement of it. If we went to I guess the optimal would be on the ground for sure, but if we could put it on, let's say, on the corners hitting the long and short side, would that be better? Or yeah, again, I just want to see what your thoughts were.
I think it's like the thing with subs is they're not very directive, so you can really put them anywhere. And if you're not getting enough bass, you could always add a couple of more. It depends on the size of the space, though. If that's, I'd like to see the size of the space. If you want to email us at technical support at toacanada.com, and I can answer your question better.
Okay, thank you.
Okay, and then the rule of thumb for how many dBs to design above ambient noise level. If we're doing an office building, normally we try to design for a 80 dB SPL, which is about the sound of a beeping alarm clock that wakes you up. So that's typically where we go for. I've typically always flown the subs from the rafters. Yep, that works too. There's nothing wrong with that. Okay, are there any other questions?
Actually, one more.
Yep.
So we usually, as a crossover, we usually use the DBX 223XS. It just separates the low and the high there. You're saying I could probably just use the TOA DSP then? Would that be kind of a good attribute or replacement, I guess?
Sorry, somebody was interfering. So you're asking if the DSP would be a good option?
Yeah, we usually use the third party crossover.
Oh yeah, our DSP is excellent. Like it's really good. So it's a digital signal processing, and you can control it from an iPad and things like that. And yeah, that'd be good. Sorry, what was the comment about the M9000 mixer? Was that a suggestion or? H Camforce said M9000 mixer, but oh, the built-in automatic resonance control. Yeah, absolutely. If you want to use the M9000 mixer, they do have for our speakers. They have built-in presets for it, but so does the DSP. I would like to recommend the 9000 because it's modular and it's good for a ton of different stuff. And
Okay.
yeah.
Thanks again.
Okay, you're welcome. And that will be all for today. If no one has any more questions, I'm going to cut the webinar now. Okay, thank you. Okay, bye everyone. Thank you.